And then, of course, we also have a team of software engineers which are developing the related software for these, but also dealing a lot with data management on different levels. Further, there is also a group of physicists. They are dealing with characteristics and investigations of devices on atomic level, and also a group of material scientists. So they are dealing with investigations of different materials, how they are characterized and how they play together. But of course, also some of them are doing simulations, because things which you cannot measure, you have to simulate to get some parameters and some characteristics of the materials. Then we do also have a group of chemists. They are mostly dealing with questions like how the environmental system can influence the behavior and the reliability of such devices, and are trying to solve these with chemical investigations. And last but not least, the group of data scientists. So this is the group where I am in. Here, as Konstantin already said, we are dealing mainly with data from the manufacturing side at Infineon. There we apply different methods in the field of computer vision, anomaly detection, pattern recognition, and so on. And the team consists right now of 11 people, and half of them also here are experienced researchers, and the other half are the students which are supporting diverse topics we are working on. And with all our projects and our work, we are mostly related to international funding projects. So with that, we are also working together with external partners. As you can see here, these are just some of them where we are collaborating on the one hand via the project itself, but of course also some of them are supervising our students from the academic side. Yeah, as I said, the KAI data science team is by now quite huge, I would say. We are 11 people. I'm also part of it, but actually I'm a statistician. And I did my master as well as my PhD at the University of Klagenfurt. And during my master, I was related to the topic of designing and implementing an optimal DOE for a predefined lifetime model. So the aim was to find the best settings for such a lifetime test at the minimum number of devices. So a minimum number of samples should be used for all these tests, because resources are always limited. And during my PhD, I then focused more in the direction of screening methods, so comparable to outlier detection, where my aim was to detect devices which have a higher probability to fail. Because of course, these devices cannot sold to the customer, but have to be screened out before they are sold or sent to someone else. Yeah, and today I'm happy to be a project manager coordinating a lot of different topics at KAI. So all the results and use cases I will present are conducted by the team. Generally, when we are talking about data science, this comprises different roles and different competencies. So mainly within a data science project, you need a data scientist, a data engineer, and the domain expert. So the data scientist is mostly related to the model development itself. So he or she has a big knowledge in the area of mathematics and statistics, but of course also in programming. Besides this, also data engineers are very important for a data science project. So their main competencies are in the area of computer science, but of course they also need to have a basic, or better, of course, more founded knowledge in mathematics. And these guys are mostly concerned with how to construct the data pipeline from the beginning to the end, and every kind of infrastructure which is involved in that. And as a third pillar in here, the domain expert, these are actually the people or the one who's providing the problem on the one hand. So this one has big knowledge, of course, in the domain where the data science project is conducted in, has some understanding about data analytics in general, and knows everything about the target scenario. So about internal processes, about business targets, use tools by the colleagues, but of course also the bottlenecks which might need to be detected. And what they all have in common is that they should have strong communication skills, because a data science project comprises different people and therefore also different levels of knowledge. So the most important thing is that these people are communicating between each other in a language everyone can understand. And as you can see here, so at KAI, we do have data scientists, we do have data engineers to construct and also to conduct such a data science project. But of course, the requirements are coming from Infineon, where they are sitting the domain experts, and then in the end, also the end user of developed models. And what's also important here is we are also always in contact with the data engineers, or let's say with the IT from Infineon side, because those people are most often the ones who then have to maintain the whole system. About data science in general, so data science is a whole life cycle, and I always try to explain this with these three pillars. So one of the areas is everything related to data, the other one related to model development and model deployment. So about data, we have to deal a lot with data governance, mainly with data management. And what also pops up in the last years is to manage even research data in a more structured way. And regarding data, we also have to consider the whole data pipeline, not just the input data for such a project, but also then the answer of the model most often is inserted again into the database with this additional information. So the whole data pipeline must somehow be considered. And what would make life easier is, of course, a unified data structure, unified interfaces, at least for one use case. So, because if you're thinking direction of scalability, all the things helps you to also sustain then in the end the whole pipeline. What's further important regarding data is data version control. So, in contrast to other software projects, for instance, not just functions, scripts, and so on have to be version controlled, but also the data itself. So at each time you should know which kind of data you have used to create your model. And then if you have to do some retraining, for instance, of course, you also have to see, okay, what changed between one or the other data set. So this should be also version controlled. And then regarding model development, there is always the question, should it be a more classical machine learning approach, or should we go into the direction of deep learning? Of course, this is somehow set by the structure of the data you can use. But also, if you want to keep interpretability, then you might go for a machine learning task instead of a deep learning one. But of course, also in that direction, a lot of research is going on to make the steps you're taking in your neural net more explainable. And when you're starting to do such a project, first of all, you do a feasibility study, but for whatever methodology you're implementing, you always have to take care that, at least in theory, this one is also generalizable, so scalable to similar data sets, similar problems, similar products. Further, we are also dealing with efficient model training. although by now we have a lot or huge computation power in which we can use, nevertheless, you always want to be efficient. And something else is also the utilization of big unlabeled data. So for most projects, labeled data is needed, but of course not. Yeah, the situation is not always given. So what we still have is a lot of data we can use, but most often they are unlabeled. So what can we do to utilize also unlabeled data for a specific problem? And with that, of course, also hyperparameter optimization excursions are always a topic. So excursions in the context of what happens if the system sees something unknown or something which was unknown beforehand, which was not covered by the training data set you currently used. So this is what we also try to figure out. Then regarding the deployment, you always have to think about what possibilities do I have to deploy then such a machine learning model. And what you can always do is you can create a standalone tool, for instance, a web application, but this then most often also means that you have to maintain this on your own. So it's always good to have a look what kind of existing environment is already given, so that you're just integrating this new feature, this new algorithm methodology into an already existing environment, because then a lot of related maintenance questions are already answered, and also related responsibilities to them are answered. Yeah, maintenance always has to be done, so no system works infinitely long on its own. Therefore, we are dealing with concepts of AI monitoring, and then here efficient retraining is even more important than efficient training, because if a model is already deployed in production, you have to assure that it's working each time also very properly. So therefore you have to be quite fast. And all these things are somehow covered under the umbrella of MLOps. So MLOps is a compound between machine learning and operations. So it's kind of a guideline of what things you have to consider if you want to bring a machine learning model into productive usage. Okay, now I want to focus on two selected use cases we are currently working on. And as I said, we do this in the framework of the IRAD 40 project, stands for Intelligent Reliability 4.0. And the ultimate goal of this project is to improve the reliability of electronic components and systems along the whole value chain. And to do so, the aim is to reduce the failure rate of these components. So here we do see that the standard bathtub curve, these components are following over the lifetime. So at the very beginning, the failure rate is high until it decreases then before it enters the so-called useful lifetime, where it's quite constant, and then it's increasing again. This is typical for electronic components and systems, but also for other settings, because you can imagine this first area here can also be called the infant mortality. So at the very beginning, you have maybe some weak, some high-risky parts which then fail. And afterwards, devices which survive this area then coming into a constant failure rate before it naturally increases again then due to wear-out failures. And with this project, each of these parts want to be lowered. We want to have a very low failure rate at each of the time. And this project is quite huge, as I said. There are 79 partners from 14 different countries, and by now we are in the middle of the project duration. So what we are always dealing is, as I said, with topics related to the semiconductor front-end production or semiconductor production. And here you can see that first of all, everything starts with a bare silicon wafer. This wafer then enters the fabrication where a lot of different steps have to be done before the product is actually finally processed. And this here at the wafer test is the first stage where you can directly measure the functionality of each of the devices on this wafer. And then, of course, here we do a first check, so to see whether all the devices fulfill the requirements. And for those which do not fulfill the requirements, they are screened out, and just the good ones are then sent to the next steps, which is the dicing. So you separate all the single devices on the wafer into single chips. These chips are then getting a package, and here again we do have a test stage where the devices are tested again before they are sent to the distribution center. And the first use case I want to talk about is related to the front-end production. So in the front-end production, the manufacturing of semiconductor devices, you're starting with the bare silicon wafer, and then you put some material on it, you do some structuring of it so that you can remove special parts again, and you're again putting on some material, and this is repeated for multiple times until the wafer is finally processed. And you can imagine that during this production, a lot of different data is recorded. So on the one hand, this is data which we call APC FDC, so data from the equipment which is processing the wafers. There you can measure things like the temperature within a chamber, or also the current which is conducted to perform this step. But also you can have some control mechanisms in between, where you're just measuring after one specific step, for instance, whether the thickness from your wafer, from your deposition step, is correct or not. And all the things are monitored and controlled, and if there is something which is not working properly, you can then or have to search for the root cause for it. What I want to focus on concretely in that case is the so-called defect density step. So at defect density, one is checking how many defects are present on the wafer, because of course defects are not wanted. So if this exceeds a specified number, then of course also here countermeasures have to be taken, and maybe the wafer even has to be scrapped. But of course, always you need to find the root cause so that you can take appropriate countermeasures. And this is what I want to explain a little more in detail. So as I said, the production of a wafer is stepwise, so layer by layer. And between specific steps, you do a defect density inspection. And not just the number of defects is important, but also the type of defect. So for a subset of these defects, in addition, also a picture is taken, for instance, these ones, to distinguish between one or the other defect. What we can see here is, for instance, a particle or a so-called pit or a crack. And by now, this classification, so which image shows which defect, is done mostly manually. And the images together with the labels are then stored into a database. But here there is a huge potential to automatize this procedure by finding an algorithm which can do this classification then automatically. And what here, or what's the biggest challenge here is, of course, not here, but for every classification task, what happens if new things occur, if new defects occur in the production where the model has not been trained for. So here we do have to find some monitoring system, some alert systems, which can then handle or at least notify that there is something which has not been seen before. And also, again, efficient updating of the model, efficient retraining, and the whole backbone needs to be defined in a proper way. You most often hear that data preparation is the most important, most time-consuming step in such a pipeline, and this is also true for this one. So as I said, for this data, there are labeled data available, or there is labeled data available and stored in this database. But for our purposes, we had to do some kind of rework. Why this was needed is, if you think of the semiconductor industry, there are different hierarchies. The top hierarchy is the so-called technology. Out of this technology, you can make different products, and each product is manufactured with different layers. And each of these layers can be inspected with the defect density, and dependent on the defects which are present there, each defect gets a defect code. And what's complicated in that scenario is that the defect codes are not harmonized over the whole technology park we do have. So what you can see in this picture, in the three examples here, is it's always the same defect in the sense that we do always see here a particle. But as you see, also the defect code, since it's coming from different products, is a different one. And this we want to harmonize. So therefore, we had some experts which were performing an additional data preparation step to bring these images in a new class structure so that we can work with them. And if we have a look on the resulting data, so for the 23 classes we do have here, you can see that the number of samples within each class highly varies. So this means that we are dealing here with an unbalanced data set. You have some classes with more images, some with less. And this is quite natural because the type of defects which occur is just not homogeneously distributed. And this is quite natural. So we have to deal with this because otherwise, as you might know, also any conclusions out of any machine learning model might be not correct. So what can we do to have better assumptions? One could choose the way of oversampling. This means that you fill up the minority classes with additional samples so that they all are more or less balanced. Or you can do the other way around. You do undersampling, where you remove from the majority classes some of the samples, but also a hybrid technique in general is possible. So we decided for this hybrid technique and first oversampled the data to fill the minority classes up, and then we also undersampled the majority classes. Doing this in the simplest form means that you're just copying data, but this is most often not really appropriate because a copy of some image means the same information again, and does not always also reflect the whole situation which could happen. So therefore, what we do also apply then is data augmentation. So for data augmentation, you have here the original image, and then you're doing kind of transformations. It could be a shear in the XY direction, a rotation, flipping, cropping, but also things like playing with the solarizing. Some blur can be put on it. You can play with the contrast and also with the noise. And all these together, of course, will influence then the actual net you want to train. So as you can see here, I was now talking a lot about data augmentation and data preparation, but of course we've done this to train then in the end a model. So for model training, by now we tried out the efficient net B0. This is also the reason why we had to do these data pre-processing in a specific way, because these nets need to have a specific input of the data. So this is why data pre-processing was necessary. And just having a quick look on the results so far. So the confusion matrix looks quite good. We achieve an accuracy of 81%, which is already quite good, but we know we can do even better. this we know because we also, for one use case, we lowered the complexity of the situation you have seen beforehand. So here we want to cover really different products, different layers, and 23 classes of defects. But if you lower these to less defects, just coming from one product, one layer, we know that we can achieve an accuracy even of 99%. So here we do see also a lot of potential for improving. And the next steps, or the next step we want to perform is that we want to try out also different nets. On the one hand, of course, from the efficient net family, but also VGG16 or ResNet 50, something like this. And this we also want to do together with the master student we are currently hiring. Okay, this was the first use case. Coming to the second use case. The second use case is related to testing in backend. And you can imagine in general, if a new product is out there, you have to qualify this product. You have to check the reliability of this final product. You have to check the lifetime. And to test these, it's always an iteration of taking some samples. They are tested and stressed alternatively. So for the stressing, you're taking these devices, you put them into a socket which is mounted on a board, and all this together then comes into a tester. So the devices are tested to see whether they fulfill the requirements or not. And then to simulate the lifetime, or to simulate what does it mean if a device is under usage, we do stress testing. And stress testing, so the setup is quite similar. Again, you have a board where you can plug in your devices, and everything is then put into a climate chamber where the stress test is performed. So stress for a device means that you have different temperatures and you're cycling the usage of these devices so that you can see whether they are reliable or not. And this is repeated for multiple times. In that area, we are dealing with 3 small use cases or 3 under use cases. One is to find a scheduler. So if you want to qualify a product, then it's defined from the very beginning which type of reliability test has to be performed. So a new project, it's called here, a new project is coming in, and then for each of these projects, you know which kind of stress test they have to follow. And this is a predefined thing which is conducted. But to schedule them in an appropriate way, you also have to deal with different workers, because not everyone can do each job. And of course, also the equipment which is related to this, because for each stress test, there are different machines which can be used in combination with different boards, different sockets. And all this information together is then inserted into a scheduler, because in the end, what you want to find out is how to utilize the equipment in an optimal way, and also which worker can do which type of stress test. So the outcome of a scheduler is then a proposal on which worker should use which machine at which time. Then another topic we are working on is related to anomaly detection. So between all these test and stress steps, the devices are taken out and pictures are taken from the devices. So this is done between each of the test stress circles. And what you find here is then you're getting images which might look like this. And sometimes it happens, and this happens really rarely, but it's important to detect if they happen, that you have some defects on it. For instance, in this first image, there is a so-called ball missing. In the second one, there is a pad missing. In the third one, you have a bent lead. And as a fourth example, there is always a marking on this device, and sometimes this marking is missing. So this also has to be detected. And by now, this is monitored by experts having a visual inspection of these data. And here we do also have a lot of potential to find a model which can do the job. So to detect exactly these anomalies. And not just to create a model, but again, we also have to consider the whole machine learning pipeline, meaning starting from the machine who's providing the data, to analyze the data, and finally also to make a kind of report from the investigation. And the machine is doing this in a way that each of these devices are put into so-called nests of a whole tray, but the AOE is not making a picture of the whole tray, it's making a picture of single frames. So in the end, what you want to have is even the single devices. But this is not feasible because this would then take too much time for the equipment to take these pictures if you do this device per device. So as a first step, we have to do here an object or train an object detector to extract the single devices before we then go on with the next step to detect the anomalies for these images. And further, the machine is also providing these images under different illuminations. This helps, on the one hand, already helps the expert if you have to do a visual inspection of them. One or the other illumination might work better for the human, and the same, of course, also for a machine learning model where we have to find out which of these illuminations is most appropriate for which defect. And in general, here we are dealing with approximately 12 different defects, but these defects happen on different packages. So we also have to consider the package itself. So because then this also means that you have to deal with different backgrounds. And this is important to know. And here we also deal with an unbalanced data set, even worse than in the example beforehand, because these failures really happen very rarely, and therefore also the amount of training data for these defects is not very high. Okay, as the last example I want to show you is related to equipment monitoring. So when you're doing qualification testing, reliability testing, or testing of any kind, you always have to be sure that the equipment you're using to perform these tests works properly. So we have here again the test equipment, and we have different components like, okay, first of all, the DAT, so the device itself, which is put into a test socket, optionally into an adapter board, to a DAT board, and then finally on the so-called load board. So here we already have some components of the equipment where each of them must be assured that it's working properly. And the same we do also have on the stress side. And the aim of this project is that we find now correlations between equipment which is failing compared to the related data one can measure during the test, between the test, and so on. So all the data which is available should be used to predict or at least to monitor the performance of the equipment itself. And for this, we are also currently searching for a master student to support these activities. Okay, now coming to the last part of my talk. Just some quick thoughts, maybe some provocative ones. The first one is more data is just more data. I heard this once, and then it took some time to think about it, because normally you always hear the slogan that the more data, the better. But of course, this depends on the problem you want to solve. This depends on the data quality you have, although data quality is also something I'm still struggling with a bit. What's more important is to choose the right data source for the right problem, because sometimes if you do not find the answer in your data, this does not mean that the answer does not exist in any data. You might have just chosen the wrong database. And then, of course, if you're getting more data, which is not useful, it will also not help in the end. Further, machines, computers do not know what's interesting. When we are conducting a data science project, then most often at the very beginning, we do know what the target situation is, what the target information is, the one the end user is searching for. So we already know in advance what is interesting for us. And now we want, instead of searching for this interesting stuff manually, we want to have a computer who's doing the job. But the other way around, this most often does not help that directly, because computers or a machine learning approach can just tell you what's in the data, but cannot interpret the result for you. A wrong attitude of expectation spoils your day. I think this is valid for many situations, but also for AI projects. I encountered that the expectations on what machine learning and artificial intelligence should do is often much higher than what we can really deliver in the end. So it's always very important, if you're performing a data science project, that at the very beginning, it's clear to everyone what does the algorithm can do, what are the limits. And then as the last one, that algorithms decide for us. Is that what we want? So by now, most of the application scenarios where we are using machine learning, we use them, or the end user is using them as a supporting system. He often does not want the system to make decisions on its own, but he wants to have a concrete look on the result and then draw his conclusion and also possible countermeasures and so on. And I think for now, this is totally fine, as long, of course, if also related legal aspects are not totally clear to that. Regarding success factors, what I encountered, or what's maybe already known by all of us, is that intensive collaboration is one of the most important key success factors, because data science is really not a one-man show, but it needs a close collaboration between all partners to bring the project to success. What's also important, of course, is faster deployment, because only as soon as the model is used into productive usage, it creates value for the company. And what also should not be underestimated are social aspects. Social aspects in the sense of the willingness of the end user also to use the system. And this can be accelerated if the end user is getting exactly what he wants to see in a way he wants to see, maybe even already in a system he's used to. And what's also important generally to mention is the attention on lifelong maintenance. So like every system, like every hardware, every software, everything in our lives needs to be maintained. And this is the same for any kind of data science and AI project, because the general opinion sometimes goes in the direction of AI should make everything on its own. This is just valid to some degree, as we might all know. But the good news in general is that we are aware of them. So awareness of all these things is again kind of key success factors. And before I'm now gonna end my talk, I want to make an advertisement or even invite you to the next Women in Data Science conference, which will take place on the 19th of May next year. So the Women in Data Science Villach is a regional initiative of the Women in Data Science at the Stanford University. And we are now conducting this in 2022 for the third time. And if you are curious on what happened the last times, there is also the recording of the live stream available on the web page, but also on YouTube. So I want to welcome you to join us maybe live then even next time at the third WITS conference in Villach next year.